This discussion is going to get into a particular form of a second-order filter. This is a low-pass second-order filter. This is often goes by the name of a Diff2, mostly because it comes out of discussions that would have been in the analog VLSI and Neural Systems book that Carver Mead developed, and was originally a conversation of trying to build a differentiator. And at the time that the book was written, that was the idea, that you might use it for that. It turned out that it actually turned out to be a really good low-pass second-order section, and there was a lot of interest there in terms of Kochler models and other kinds of spaces. So for multiple reasons, people care about it. Now, for the astute circuit designer, you'll look at this topology and go, maybe this is a form of what is typically called a Tau-Thomas type of topology, and the answer is yeah, that actually would be true of a topology that you typically see with resistor and capacitor type networks in its canonical structure. So there is definitely similarities here. The core of the structure is basically imagining I have two OTAs. Again, I may have the voltage bias that I can control in these cases, which then would set whatever its transconductance is. Now these might be physical biases. These are things that may be loading case that you're setting it. A number of things are possible. And if you look at the structure, what you actually have is the first element here basically looks like an integrator, a high gain structure. And the second structure basically looks like a low-pass filter, unity gain type of topology. And then I build the feedback all the way around it. One could imagine this is actually an interesting model for talking about things like op-amps and other topologies where maybe I have an op-amp where I actually buffer it, or I have an op-amp that has another stage. And so there's a very typical question that comes into the stability of these kinds of structures. You might even imagine this would be having an input running through two stages, depending on if I were to connect this across or maybe have an open gain. I could actually ask what kind of structure would that look like. But for this particular one, we get a particular type of topology, and if I do, my second order filter will look something along the lines of sort of canonical low-pass form with both the tau squared at the s squared and tau over q for s. In this case, for this topology, a little bit of math will show you that you can actually get the tau is interestingly the square root of those two taus. And it's the tau that I would get by looking at this as an integrator, the tau I would get here from low-pass filter. So the tau here would simply just be what is its capacitance over its transconductance. And again, the same sort of thing here would be the load capacitance, would be related to the load capacitance and the transconductance as well. The Q, interestingly enough, is related to the ratio of those two taus. That actually opens up some other possibilities for this. Certainly, if I was asking for a very simple, stable system and both of these were equal, I would be looking at a Q that's 1, or that would now give me something right about at resonant. I get something sort of at resonance. It would mean I get certainly a significant more phase shift. But I can use the structure to tune and get very simple frequency responses, or I can get things with a very interesting Q, like here a Q of 5 with this particular tau, and I get a nice 40 dB per decade roll-off no matter what I get there. The gain will be 1, and then depending on the value for Q, this will either just roll, or I'll start to get some sort of peaking as a result of it. Now, I typically like looking at the step response for a case like this, and this would be a similar case. It turns out to be relatively a similar Q, slightly different frequency corner. And you put in a step response, typical good way to look at this. I think so much people would prefer to look at frequency response because that's what we're trained as double A's. On the other hand, there is a lot of information to be gleaned from the step response, and we shouldn't actually ignore that as we're putting it together. So if I were to look at that and actually look at the step as I were to step down a direction, what I'm going to find is that its trajectory is going to oscillate all the way back to equilibrium. When I step up, it'll quickly get there, but it overshoots, typical of a higher Q, and takes some time before it settles down. If you want to think about it as disturbing a harmonic oscillator, same sort of dynamics all the way through the system. So this turns out to be a very useful structure, very easy to be able to tune this in a number of other forms. Certainly one could get into many more conversations as we go through this, but this gives us a good starting point in terms of where we are going forward.